Hello guys, in this video I'm going to summarize all the chapters which are already covered during my lectures for week number 1 until week number 5. In addition to these summary documents, you also will be able to access the previous and also current assessment in the Google Drive folder, which the links is available as follow. The the previous assessment includes the final exam question for the previous semesters together with the assignment and also tests. Alright, let's move on to the content of my topics. During our first week of lectures, we are covering for the chapter number 1, which is an introductory chapters. In this chapter, we learn about the importance of the process control in industries, and also you should be able to identify the control variables, manipulated variables together with the disturbance variables. Example of this type of assessment can be seen for the test number 1, question number 1A, together with the previous semester final exam question, which is question number 1A. In addition, the control strategies such as feedback control and also feed-forward control were also introduced. So I still remember that during the Plan Design 1 presentation for the group number 2, the panel from the industries did ask regarding the control system. So supposedly you should say that the control for the process control is actually will be covered in the Plan Design number 2. Example of the assessment for the control strategies include test number 1, question 1B, assignment, and also previous semester final exam question for question 1C. This one I'm not going to cover in detail in this video. You can always refer to the previous video, or you can refer to the sample of assessment, which is also can be accessed through the Google Drive. And then once we completed with the chapter number 1, we move to the chapter number 2. So for the chapter number 2 over here, we learn on how to develop the mathematical model for the chemical processes. Ideally, we want our chemical process in a steady state, but in reality, it is almost impossible for us to have the steady state throughout the operation. Thus, process control come into the pictures. So see example 2.1 together with the assignment 1, question number 2. Example 2.1 will be discussed later. And then in the chapter number 3, we actually revisit or reintroduce to the Laplace transform, which already been learned during your Maths 2. The main purpose of knowing of this, sometimes we end up with the complex ordinary differential equation, as seen in the example 2.1, when we try to analyze the rate of change of the liquid level inside the tank. Thus, we need to convert the ordinary differential equation into the Laplace functions with the S domain instead of T domain, and then we need to convert it back to the time domain by using the inverse Laplace. This one I think also will be covered in the example 2.1. And then the last chapter for my part is actually on the transfer function. So for the transfer function over here, for my part is just an introductory parts, meaning that later during your lectures, actually you're going to learn in detail about the transfer function. The important thing for the chapter number 4 is the deviation variables. This one I will discuss in detail for the example 4.1. So now I'm going to move to the two examples which I'm going to discuss in this video. So example 2.1, a stir-time blending process with the constant liquid hold-up of 2 meter cubes. So meaning that this one is going to be my V equals to 2 meter cubes, is used to blend two streams whose density are approximately 900 kilograms per meter cubes. The density does not change during the mixing, so we can say that here we are saying that the density is constant. Alright. assumes that the process has been operating for the extended period of time with the flow rate of W1 equals to 500 kilograms per minute and W2 equals to 200 kilograms per minute, and then the feed composition or the mass fraction of the X1 equals to 0.4 and X2 equals to 0.75. What is the steady state value of the X? So to start, to answer this question, usually I will start with the drawing a simple diagrams. So let us draw a simple diagram for the blending system. So now they're saying that we got two different streams for the blending system. So let's name it as a stream 1, here as a stream 2, and then both streams are going to be mixed in the mixing tank, and then the mixture is going to come out in here. Let's we use W and X. W is the mass flow rate, yeah. So here, because the stream 1 is going to be W1 with the mass fraction of X1, here is going to be W2 with the mass fraction of X2. I'm going to write down the information given. In here it stated that W1 equals to 500 kilograms per minute. So W1 equals to 500 kilogram per minute. This one is given, yeah. And then the X1 equals to 0.4. This is the mass fraction. And then we have W2 equals to 200 kilograms per minute. You can always refer to this one because I'm going to share the summary documents with you later. And then we have X2 equals to 0.75. And then the question asking for what is the steady state value of X. We need to find the value of X. In here, we assume that is a steady state. So usually I will start with at the steady state. At the steady state, we learn that whatever is coming into the system, so basically this is the system, should be equals to whatever come out from the system. So I will say that if I have 5 kilograms entering through the stream 1 plus 200 which is entering through the stream 2 should be equal to whatever come out at the exit stream over here. So if you notice that, because it was a steady state, therefore I'm going to use a W1 bar, W2 bar, and also W bar. So I'm going to rearrange it. I'm going to get W bar is actually equals to W1 bar plus W2 bar because it was a steady state. And then I'm going to put a value over there. So it is going to be 500 plus 200. So now it's going to be 700 kilograms per minute. This one should be straightforward, yeah. Maybe you already forgotten that what does bar mean. Bar mean here, this bar actually refers to the steady state. For the steady state process, there's no mass accumulated, which we're going to discuss later. Alright, so now this is the overall balance. So in here, if you take a look at the information given over here, obviously this is actually a mixture. If you notice that the X1, the mass fraction of the component 1, mass fraction is actually equals to 0.4 in the stream 1 here. Same goes for here. The mass fraction in the stream 2 equal to 0.75, means that let's say for the stream 2 here, we got two different components, component A and then component B. So most probably component A, the mass fraction will be 0.75, while remaining 0.25 is the mass fraction of the component B. So in here, I can always take a balance for the component A. Let's assume that it is a component A. The information given is for the component A. So now I'm going to say that balance for the component A is actually equals to W1 bar multiplied by X1 bar plus still the same, yeah, because it's still at the steady state. W2 bar multiplied by x2 bar, because I'm considering for the component A, equals to W bar multiplied by the X bar. So now the W1 bar is given, which is 500, multiplied by 0.4, which is mass fraction, plus W2 also given, 200, multiplied by the X2, which is mass fraction of component A in the stream 2, 0.75, equals to W, which we already calculated before, 700, multiplied with the X. So now I can say that X is actually equals to 500 multiplied by 0.4 plus 200 multiplied by 0.75 divided by 700. So now I'm going to get the value of X bar equals to 0.5. Meaning that at the outlet stream over here is going to consist 0.5 or 50% of the component A. So we are already done for the part A here. Now I'm going to move to the part B. I'm going to erase some of the calculation here because already calculated for the steady state. So it's going to be erased. This one also going to be erased. I'm going to redraw the diagrams. Let's make it look something like this. Alright, so now for the second part of the question, suppose that W1 changed suddenly from 500 to 400 kg per minute and remains at the new value. Determine the expression for the xt. What does it mean here? Means that before this, we assume that throughout, let's say I'm going to run the blending process over here, let's say for 48 hours, meaning that 2 days I'm going to run it straight away. So before this, what we want here is, it is a steady state, meaning that whatever is coming, let's say I have 500 is coming from the stream 1, 200 is coming from the stream 2, and then we're going to end up with 500 plus 200, 700 throughout the process. But as I said before, it is almost impossible for us to have the steady state process for the chemical process. I mean, almost impossible for us to have all the time we're going to have the whatever is coming equals to whatever is come out. Almost impossible for in the real life or in reality. Therefore, sometimes we're going to have, suddenly we found that, just like example B here, we found that after some time, instead of it the flow rates at the stream 1 here maintaining at 500, suddenly it was changed to 400 kilograms per minute. So once it's changed to 400 kilograms per minute, it is no longer steady state process, because now the flow rate already been changed to 400 instead of 500. Therefore, because it was not steady state process, therefore, since it is unsteady state process, therefore we have to consider the rate of mass accumulated. The rate of mass accumulated usually represent mass equals to dm. Rate should be over time. Rate of change of mass equals to whatever is coming. In this case, is going to be W1 plus W2 minus whatever is come out. So in this case, I can say that this is the in, this is going to be an out. Even from the diagram itself, you should notice that the in minus out should be the rate of mass accumulated. And then if I'm going to consider this one that is the overall. If I want to consider for the component A, now my equation should look something like this: dmx over dt equals to w1 x1 plus w2 x2 minus w multiplied by x. If you notice that here also we no longer have the bar, just like previous example, just like something like this. We no longer have this one because it is no longer a steady state process. So now I already have this equation. Rate of change, or I mean the rate of mass accumulated inside the system over here, so meaning that some of it will be stay inside the system over here, equals to in minus out. And also, if you notice that in the question here, it doesn't mention about the mass. No mass mentioned about it at all, but they did mention about the density. Therefore, I need to use whatever information is given. In this case, they gave me about the density. I also know from the fluid mechanics, density, it is actually equals to mass divided by volume. If I'm going to rearrange it, I'm going to say that mass is actually equals to density multiplied by the volume. Therefore, I can substitute this equation into my new equation over here. So now I'm going to end up with a rate of change of rho multiplied by V multiplied by X divided by dt equals to W1 X1 plus W2 X2 minus W and X. But also it's stated that the constant liquid or the volume is constant together with the density. Density also constant. Yeah, the density does not change during the mixing, therefore the density is constant. Because it was a constant, it doesn't change, therefore there's no d rho v. Therefore I can take out the rho v over here. Rho multiplied by v dx over dt equals to w1 x1 plus w2 x2 minus wx. Because here the question is actually asking for what is the express xt, meaning that what is the value of x which respects to t. What is the composition of x in a function as a function of t. So now I already have something like this. This one is just derivation actually. So now I have a rho multiplied by v multiplied by dx over dt equals to w1 x1 w2 x2 and also w minus x. Let me think how to move forward from this one. Okay. I'm going to rearrange this equation. Yeah. So now I'm going to have rho multiplied by v dx over dt plus, I'm going to move this to other side, plus wx equals to w1 x1 plus w2 x2. Now I'm going to divide all the term with the w. So now on this side I'm going to have rho multiplied by v divided by w dx over dt plus x equals to w1 x1 plus w2 x2 divided by w. Why? Because from chapter 7, which is you learn it subsequently, rho multiplied by v divided by w is actually equals to time constant or tau. So now I can say that my equation can be further simplified as tau dx over dt plus x equals to w1 x1 plus w2 x2 divided by w. Now I'm going to substitute the value. Yeah. So actually I can calculate what is my value of tau here. So the tau here equals to density. The information is given. Density equals to 900 multiply with the volume, which is v, multiplied by 2 divided by W. But then the W here is no longer W bar, because the W here is a new W. So now for the part B here, I have W1 equals to 400, W2 equals to 200. So I can say that W equals to W1 plus W2, which is equals to 400 plus 200, which is equals to 600. So now I can say that my W should be 600 dx over dt plus x equals to W1 should be equals to 400 multiply with the x1, which is 0.4 plus W2 should be 200, and then x2 should be 0.75 divided by W, which is previously calculated 600. So now I'm going to end up with tau equals to 1800 divided by 600 equals to 3 dx over dt plus x equals to I'm going to solve for this one. I'm going to end up with 0.517. So this is, if you notice that, this is the relationship between the x with respect to time, meaning that as the time changes, the value of x also change. But then this one is very difficult for us to imagine, yeah, because at the t equal to 0 is very difficult for us to calculate. That's the reason why we let it in chapter number 3 to use Laplace. That's why we have to use a Laplace to convert it into the S domain, and then reuse the inverse Laplace to convert it back to the times domain. So I'm going to try to do solve for this one, yeah. So I'm going to take a Laplace for every single term. Laplace for 3 dx over dt plus Laplace of x equals to Laplace of 0.517. So taking a Laplace for the 3 dx dy, I'm going to get 3 multiplied by s, x function of s, minus x0 plus Laplace of the x is going to be x function of s equals to 0.517 divided by s. So this is going to be my Laplace function. And then you should notice that the x0, what does it mean? Meaning that what is the composition in the beginnings before we start our operation? We can say that for the x equal to 0, it is actually equals to steady state, because initially for the part A, it said that okay, the process was steady state. After you run it for, let's say, 72 hours, you found that now the W1 was changed. The X1 was the W1 was changed, therefore it's no longer steady state. But in the beginning, the x0 here is actually equals to x bar, which is we calculated before, which is 0.5. Therefore I can substitute into here to get 3s x function of s minus 3 multiplied by 0.5 is going to be 1.5 plus x function of s equals to 0.517 divided by s. Now I'm going to factors the xs, yeah. So now I have xs 3s plus 1 equals to, I'm going to move this to the other side, is going to be 1.5 s plus 0.517 divided by s. So now I have xs equals to 1.5 s plus 0.517 divided by s, 3s, let me undo it, s multiplied by 3s plus 1. This is in the form of Laplace. So I'm going to use A over S plus partial fraction 3s plus 1, and then I just assume that first I assume S equal to 0, then let S equal to 0. This one already been covered during our test and etc. S equal to 0. So now I'm going to get 0 multiplied by plus 1 is going to be 1, multiplied by A is going to be A equals to 0, A equals to 0.517. Then I'm going to say that let S equals to negative 1/3. Now B is going to be negative 1/3 multiplied by 3 is going to be negative 1 plus 1 is going to be 0. A is going to be 0, and then S is going to be negative 1/3. So now it's going to be negative 1/3, 0.5, 0.017. The B is going to be 0.017. Therefore, I can write down my Laplace expression as below. So I'm going to get 0.517 divided by S plus 0.017 divided by 3s plus 1. So now to get the expression for x as a function of t, it is actually equals to inverse Laplace of the 0.517 divided by s plus inverse Laplace of 0.017 3s plus 1. So inverse Laplace for this one, it is actually equals to so now I'm going to get 0.517 because inverse Laplace for this one is going to be 0, the numbers itself, and then plus this one I should use the number 6. So I'm going to get 0. Does it no 0.017 divided by 3 e to function of negative 3 negative t over 3. So this is the expression of my xt. Comparing to this one, if you compare to this one is very difficult for us to measure what is the composition of the outlet stream here. I mean, what is the composition of the outlet stream here, which is x, by using this ordinary differential equation, see? But then compared to this one, if you notice that, let's say I want to find what is the composition or x at t equals to, let's say, equals to 10. I just simply substitute the value of t equals to 10 over here. Then I can calculate what is the value of x for the x equals to 10. X equals to 10, I just simply substitute 10 into here. And then I can plug in the value here, calculate, and then I'm going to get the value here. Compared to this one, see? Because this one is the ordinary differential equation. Very hard for us to imagine how do we get the value of x at any given t. So that's why we have to use, what we have to do here is, usually we're going to end up with the ordinary differential equation, and then we're going to use the Laplace in order for us to get x as a function of s. But then x as a function of s is not very useful to us because usually we use the time domain. Therefore, we have to convert it back to the linear time domain, and then we're going to end up with the x as a function of t. Easier for us to measure it any given time. Let's say time t equals to 5. T equals to 5, we just simply substitute t equals to 5 into this equation, t equals to 5, and then it's going to be e to power of 5 divided by 3 negative multiplied by this one, and then plus this one. Then I'm going to able to calculate what is my mass fraction of the component A for the t equals to 5, t equals to 10, and etc. as compared to the ordinary differential equation. So this is the example 2.1 over here is quite useful for us, so that we can have some general idea why the Laplace transform is important. And also we should note that we should be able to differentiate between the steady state process, meaning that whatever is coming through the blending process over here should be equal to whatever come out. And also, but as I said during my summary before, usually in the real life, for the industrial process, usually it's almost impossible for us to have a steady state process throughout the operation. Always, sometimes due to the disturbance and etc., we're going to get the unsteady state process. Because of this unsteady state process, that is where the process control important, because sometimes we want to make sure that the value of the composition here doesn't change much. For example, let's say you're using process control, you want to make sure that the composition is always maintained at 0.4. Suddenly, after some time, you notice that suddenly the x1 here was actually increased instead of 0.4 to become 0.6. So this is where the process control come into the pictures. Yeah, I think already done for the example 2.1. Now I'm going to move into the example 4.1. The example 4.1 here is all about the transfer functions. By now, I hope that you should be have clear pictures of what the transfer function is all about, because usually the later chapters you did use a lot of transfer function. So let me erase it first, then we can move on to the okay, example 4.1. Consider a stir tank blending process for figure 1 above, which the W1 equals to 600 kg per minute, W2 equals to 2 kg per minute, and X1 equals to 0.05, and X2 equals to 1, or pure solutes. The liquid's volume and the density are constant. This one, in fact, they already mentioned about the V, and also the rho constant, which is V equals to 2, and then the rho equals to 900 respectively. Derive the expression for the transfer function for both inlet 1 and 2. See, this one they're asking for the transfer function. So now I'm going to move into the transfer function, because in the summary over here, see, they just mentioned about that usually the transfer function we use deviations variables. So to start this one, usually I will start with the with the basics introduction of the transfer function. So I'm going to use whatever I already derived before in the example 2.1. So for the unsteady state, I should have rho multiplied by V dx dt equals to W1 x1 plus W2 x2. So meaning that this is for the stream 1. So if I'm going to draw, it looks something like this. So this one is stream 1. This one is going to be my stream number 2. And then it's going to be blend together, come out as the W and X. So now this one is the entering into the system minus out from the system. And then I'm going to move it around, meaning that I'm going to move this expression terms on the right side. So I'm going to get rho V dx over dt equals to W1 x1 plus W2 x2 rho V dx over dt plus Wx. But then I don't want W, so I'm going to divide all terms with the W. So now I'm going to have rho V divided by W dx dt equals plus X equals to W1 over W x1 plus W2 over W multiplied by x2. By now, you should know that W1 divided by W is actually what we call a gain, represented by the symbol K1. This one is covered in the chapter 8, I think. W2 divided by W is actually another gain for the stream number 2. So usually we just simply represent the symbol K1 and K2. K1 meaning that the stream 1, K2 referring to the stream 2. Rho multiplied by V divided by W is actually equals to tau, time constant. So now I can write down here is as tau dx over dt plus x equals to K1 x1 plus K2 x2. But then, as I said before, so if we take a look at this expression or this equation, what does it mean? Meaning that this one is actually x1 is actually the mass fraction of the component A in the stream 1 at any given time. But in order for us to develop the transfer function, actually we're interested with the deviation variables, because usually the transfer function was described as a deviation variables. You will see later what does deviation variables mean. Yeah, for the time being we're going to derive first. So let's say here I can say that deviation variables for the x1 equals to x1 for any given time minus the value of x at the steady state. Same goes for the x2. Deviation for the x2 equals to x2 for the unsteady state minus the steady state. Same goes for the x, which is equals to x minus x bar. X1, x2. So now, instead of using the mass fraction of any given time, I'm going to use the deviation. So now I'm going to have tau d x prime over dt plus x prime equals to k1 x1 prime plus k2 x2 prime. So now I can do the Laplace, because usually for the transfer function it is as a function of s. So now I'm going to say that I'm going to take a Laplace for every single term over here. Taking a Laplace of the d x prime over dt, I'm going to get tau multiplied by s x prime s minus x prime 0 plus Laplace of the x prime is going to be x prime s equals to k1 multiplied by x1 prime as a function of s plus k2 x2 prime as a function of s. And then of course initially we assume equals to steady state. Therefore for the steady state is going to be, let's say here I want to calculate what is my x prime. So here my x prime equals to x minus steady state. So if the initial value was steady state, so here x is going to be s bar minus s bar is going to be 0. Therefore I can say that my x prime s, my deviation, was actually equals to tau s plus 1 equals to k1 x1 prime s plus k2 x2 prime s. Or I can write here as s1, the deviation of the outlet for the component 1, the component A, equals to k1 divided by tau s plus 1 x1 prime plus k2 tau s plus 1 x2 prime as a function of s. So this is, so this is actually the transfer function for the stream 1, and then this one is going to be transfer function for the stream number 2. So this is how what it's about. I do understand that before this we have x bar. Now we're going to have x prime. So the x bar here should be straightforward, steady state. X only, meaning that it is unsteady state. The deviation is actually reference to the x bar. X prime here are referring to the deviation. We can take a look at this example. This example is a good example for us to have a better understanding what does the x prime means. Yeah. So let's try a question. Alright. So that we can have better understanding what does the deviations means. Okay, I'm going to move to this question. Sorry. Alright, I'm going to start with the example 4.1 part B. Okay, given that, okay, so I think the best way to start with this one is actually to draw. So I'm going to draw it. So I'm going to have stream 1 with the mass flow rate of 600 W1, and then I have X1 with the value of 0.05, and then it's going to mix together with the stream number 2 with the W2 equals to W2 equals to 2 kilograms per minute, and then with the X2 equals to 1. So X2 equals to 1 means that in the stream 2 here, we only got component A, no component B. But in fact, for the stream 1 here, we have X1 equals to 0.05, meaning that majority of the stream, of the component of the stream 1 here is actually is not an A, but something else. So now they're going to mix together, and then they're going to come out here as the new flow rates together with the new mass fraction. Okay, so we already done the basic diagram over here. Derive the expression of the response xt, meaning that we want to find what is the value of x. What happens to the xt here? How does xt change for a sudden change in the x1? Meaning that the x1 here is going to suddenly change. Instead of 0.05, it's going to change to 0.075, meaning that now the composition has been changed for the stream number 1. This is what the statement is all about. Initially, we can assume that it is at the steady state. So what we can do over here was we can assume that, okay, initially we can start with, because it stated that initially at the nominal steady state. Initially we can say that at t equals to 0, I can say that W equals to W bar equals to W1 bar plus W2 bar, which is equals to 600 plus 2 equals to 602 kilograms per minute. This is before the changes of x1 occurred, and also I can calculate what is the steady state value for the x. So I'm going to use, just like before, W1 x1 bar plus W2 x2 bar equals to W and x, so that I can say that x bar at the steady state value, the value of composition of x in the outlet stream equals to W1 bar x1 bar plus W2 bar x2 bar divided by W bar. W bar has been calculated above. So W1 equals to 600 multiplied by 0.05 plus 2 multiplied by 1 is going to be divided by 602. And then I'm going to get the value of x bar equals to 0.053. So this is the value of composition of component A at the steady state. So I think this one should be straightforward. Everybody should be able to at least calculate for this one. So now what I want to do here is I want to calculate the sudden change in the xt here due to the changes of the value of x1. So usually I will start with something like this. I will say that the deviation of x1, how much x1 is deviate from the original steady state value, it is actually equals to, before this I already erased that one, but then the formula is just the same. The deviation of x1 equals to the value of x1, the original value, the new value minus the steady state value. What is the new value of the s1? It is actually equal to 0.075. The steady state value, it is actually equal to 0.05. So now my value of x1, it is actually equal to 0.025. You should ask yourself, the x1 here, 0.025 here, as a function of, definitely it is actually as a function of time. So I can also write here as deviation value of the stream 1 as a function of time equals to 0.025. So that I can say that x1 prime as a function of s, which is taking a Laplace for this one, I'm going to get the value of 0.025 divided by s. Later you will see why I use a Laplace, because I want to take transfer function. Okay, so now I already got this value. So before this, I already derived something like this. I have deviation value as a function of s equals to k1 divided by tau s plus 1 divided multiplied by x1 as a function of s plus k2 tau s plus 1 multiplied by x2 prime in the function of s. This one is actually I derived for the question 4.1 part A. I already derived before, so I end up with this one. But I also noticed that for the stream 2 here, the x2 here is actually equals to 1, meaning that for the stream 2 only have component A. Therefore, the deviation of the component A is going to be 0. For this one, depending, sometimes you can have the x2 here is not equal to 1, maybe 0.5. Because it was 0.5, therefore definitely is going to be deviate from the original steady state value. Therefore, now I'm going to end up with this one only. So now I have x1, x prime s equals to k1 divided by tau s plus 1 multiplied by x1 s. Also, if you remember that the k1 here is actually equals to w1 divided by w1 given in the question, it was 600 divided by w, which is 602. Then I'm going to get the value of k1 equals to 0.997, which is k1 is a gain for the stream 1. Same goes for the tau. Tau is actually equals to rho multiplied by v divided by w. Rho is actually given in the question 900 multiplied by 2 divided by w, which is 602. So now I'm going to get tau equals to 2.99. So I can see that tau is almost equals to 3. I can use 3 as my tau value. Then I'm going to substitute the value of k1 here, also tau, into this equation. So now I have x prime s equals to 0.997 multiplied by the divided by 3s plus 1 multiplied by the x1 prime. What is the deviation value of the x1? See, this one as a function of s, because before this I do get as a function of t, 0.025. Therefore, the x1 prime as a function of s equals to the Laplace function of this one, which is 0.025. So it's going to be 0.025 divided by s. So now I'm going to multiply these two. Multiply by these two, I'm going to get 0.997 multiplied by 0.025. I'm going to get 0.249 divided by s, 3s plus 1. So this one should be straightforward to solve. I can either use a partial fraction, or I can also use number 13, because in the number 13 it stated that inverse Laplace of 1 divided by s tau s plus 1 should be equals to s as a function of t. The 1, you can refer to the Laplace table, equals to 1 minus e to the power of negative t over tau. So I can straight away use number 13 here, because I have function looks something like this. Therefore, I can say that my deviation value of xt was actually equals to, I'm going to Laplace it, and then I'm going to get this value. So it's going to be equal to 0.249 multiplied by 1 minus e to the power of negative t divided by 3. So I can write down here as the deviation value of 0.249 equals to 1 minus e to the power of negative 3 over negative t over 3. To understand the what does deviation mean, so let's say so I'm going to draw much more simpler. Let's say I want to control, let's say this time instead of controlling the x, which is mass fraction, let's say I want to control the height over here. So let's say I have a 2 stream, but then I always want to make sure that my height was actually equals to, let's say, h. So ideally what I want here is, let's say I'm going to run it from t equal to 0 until t equals to 1000 hours. So ideally what I want here is, I want to make sure that my liquid level, because this one is going to be my height, which is height of the tanks over here. Ideally what I want here is, let's say h here equals to 10, so this one is going to be 10. Ideally what I want here, I want to make sure that the level is always maintained at the 10. Just the graph should look something like this, but in reality sometimes what happens here is it is actually deviates, looks something like this, which is you already learned with the Shira, right? So this is what we call the deviation, meaning that it's not necessarily to be, but it's almost close to the height. Usually it is a control action making it to try to return back to the state value. So this is what we call a deviation, while this one is what we call the h. 10 here is going to be h bar, but then the value here is going to be h, and then the difference between the h and also h bar over here is what we call the deviation. So I hope that this video, my nose already started to run a lot now, so I should stop with this video. I hope that this video should be able to help you to have a better understanding and prepare for the finals. Good luck, guys.